All right, now we need to talk about the Sn1 mechanism, but before I get into the details of the Sn1 mechanism, I'd like to talk a little bit more thoroughly about the nature of the leaving group. In a lot of these reactions, you're going to notice that the leaving group is a halide. But we can also have protonated alcohols, or we can have negatively charged oxygen atoms that are making a bond to a group that is stabilized by resonance. The quality of the leaving group is actually addressed in one of your PowerPoint slides, and I'd like to emphasize that at this time. So on slide 1 of your notes, notice that there are two important qualities of a leaving group. Quality number 1 is it simply has to be more electronegative than the carbon atom to which it's attached. We're talking fluorine, oxygen, nitrogen, chlorine, bromine, iodine, and sulfur. But criteria number 2 is also very important. It has to be able to stabilize the electrons with which it leaves. So in this context, something like OH minus is not a good leaving group because it's really not capable to be stable without it coming back and re-reacting with the carbon electrophile. So let's talk about ranking some of these. In terms of halides, the larger halides are going to be the most stable. So iodide is a better leaving group than bromide, which is a better leaving group than chloride, which is a much better leaving group than tiny fluoride. Also, if we have an alcohol as a reactant, it can undergo the Sn2 or the Sn1 mechanism, but we typically would need to react it with an acid. And the whole idea of reacting it with a strong protic acid would be to convert it to a better leaving group. So in this example, I have a positively charged oxygen. If I were to attack with a nucleophile now, water is a much better leaving group. We will add to this pool of knowledge as we go on. There are also some very nice chemical substitutions that we can do to OHs so that they can be resonance stabilized. And I think what I'm going to choose to do is to simply discuss this a little bit later in the course, but it's something that we'll definitely get to before the end of the semester. So let's talk about the third logical possibility that we can have in substitution reactions. And that is possibility number 2. Loss of the leaving group occurs first, and then nucleophilic attack. For example, One of the lab experiments that we'll be performing rather soon is we are going to begin with T-butyl bromide. And we are going to react this with water. Now, water is our nucleophile, but in the first step of the reaction, we actually break the carbon-Br bond. This leads to an isolable intermediate, carbocation intermediate. And then a lone pair on the oxygen atom is nucleophilic to alleviate the charge. Notice the oxygen will have a positive charge. And now the Br minus leaving group can neutralize this compound. Of course, HBr is a side product. We're not real concerned with that. And give us T-butyl alcohol. Or more appropriately, 2-methyl-2-propanol. This is the Sn1 mechanism. So let's look at what the potential energy diagram would look like. Again, we're going to have enthalpy as a function of reaction coordinate. Energy of our reactants. Intermediate, second intermediate, energy of our products. We have three energies of activation, three transition states. Transition state number 1 is the carbon-bromine bond beginning to break. Of course, bromide will have partially negative charge, whereas the carbon that is forming the carbocation will have a partial positive charge. First intermediate is this tertiary carbocation. Second transition state H2O and a pair of its electrons beginning to form an oxygen-carbon bond. Second intermediate, the bond has been formed and there is a positive charge on the oxygen atom. Third transition state, oxygen-hydrogen bonds beginning to break. Hydrogen-bromine bond is beginning to make. Unlike in the Sn2 reaction, in our Sn1 reaction we have discrete steps and isolable intermediates that we can characterize through spectroscopy. So notice in an Sn2 reaction there is only one transition state. In most reactions, you could perhaps have two if you had to activate the leaving group by protonating an alcohol. But an Sn1 reaction is always going to have more steps than an Sn2 reaction. Let's explore what Sn1 means. In Sn1, the rate of the reaction is dependent by what happens in the slow step. We can easily identify the slow step by looking at the energy of activation. The slow step is not always the first step, but it is always the step that generates the highest energy intermediate. The carbocation is higher in energy than the protonated oxygen because there's no octet of electrons in intermediate 1, whereas there is an octet of electrons in intermediate 2. So energy of activation for step 1 is much greater than energy of activation for either step 2 or for step 3. Step 2 and step 3 are essentially irreversible. They are not at equilibrium. The first step is very much at equilibrium, and it has a choice of falling off and going back to reactants or going to the intermediate to generate products. The driving force for it going to the intermediate is the eventual lowering of the energy state to give a negative delta H. So in the slow step, the only thing that we have is dissociation of the leaving group. And so this reaction depends upon the concentration of the substrate only, and this is why it's called Sn1. It's substitution, nucleophilic, unimolecular. There is no collision in the slow step. There is only the energy that is absorbed for this bond to break. Now this bond is not labile enough to break in the absence of a nucleophile or a solvent, but the nucleophile and the solvent together encourage this bond breaking process by being able to stabilize the leaving group as it goes away. Also, we know bromide is a really large ion and is able to maintain a stable existence even though it has an integer negative charge. These are all aspects I'll be talking about in class in much more detail. So let's take a look at how Klein addresses this. First of all, notice the stepwise mechanism, which means it occurs in steps. In step 1, the leaving group dissociates. This is the rate limiting step to give this intermediate carbocation. Notice he also has a tertiary substrate as his example. This later will become significant because we will learn that, of course, tertiary carbocations are going to be much more stable than secondary, a fact and a series of observations that we've emphasized previously in class. And in the second step, we have nucleophilic attack to generate our new product. It's Sn1 because we only depend upon the concentration of the substrate, which would be our reactant molecule. So this would go neatly into the concentration brackets in the integrated rate law expression. If we look at a typical Sn1 reaction coordinate, the one that I did earlier is a little different only because our nucleophile is negatively charged and we don't need to neutralize the compound. But notice the first step, generating the carbocation, is going to be the rate limiting step because I don't have an octet of electrons. the intermediate is isolated, and the nucleophilic attack has a very small energy of activation barrier. Also notice that, like all substitution reactions, it's going to be an exothermic reaction and not an endothermic reaction. This makes sense because we start with two particles, we end with two particles. We know the entropy is not significantly changing in the reaction. Now let's take a look at another interesting aspect of this reaction. Let's look at the stereochemistry outcome. We already accomplished this for SN2. Let's now look at SN1. The mechanism is going to be our guide as to what we should expect in terms of a stereochemical outcome. And what I'd like to do is use our previous example. After the leaving group dissociates, so once this dissociation occurs, boy, I had trouble saying that, didn't I? Dissociation. I have a carbocation intermediate. Now, with the carbocation intermediate, all of these methyl groups are going to be in one plane. We have an empty p orbital. Again, this is sp2 hybridized. That means we have a p lobe that directly comes towards us out of the plane of the screen, and a p lobe that goes away from us directly into the plane of the screen. The nucleophile really does not attack the electrophilic carbon. It attacks the empty p lobe, and it can either attack the p lobe coming towards us or it can attack the p lobe coming away from us. Now remember, when we attack, and we learned this from SN2, if I attack from the front, it's going to push the methyl groups to the rear. And if I attack from the rear, it's going to push the methyl groups to the front. In this particular substrate, there's not a stereochemical consequence, but we can visualize, if there was, that we would get an equal amount of the nucleophile being oriented directly towards us or the nucleophile directed completely away from us. This means that we have a racemic mixture. If R and S is possible, we would get 50% R and 50% S. Unless there is significant steric bulk that blocks one of those spaces. Let me give you an example of that. So with this particular alkene, you have to realize that this whole bulky group is popping towards the top. Once I make the carbocation intermediate, I will only be able to attack from below the plane. Attack from above the plane is going to be prohibited. So if you have something that's significantly bulky, significantly complicated, you will not get 50-50. You will have one of those enantiomers that will be selectively made. This is called a stereo selective reaction. And we'll certainly see applications of this in the very near future. But all of the things being equal, and certainly in the case of where I simply have 3 methyl groups, I will get the racemic mixture. Simply should not be expected to happen in all circumstances. Now, because our substrate are so different and we can make different types of carbocations, we should expect there to be a substrate selectivity. And the selectivity for Sn1 is really the opposite of the substrate selectivity for Sn2. This also shouldn't surprise us because we know fundamentally we are making bonds, breaking bonds with different steps, different sequences, and also different rates. In Sn2, everything pretty much occurs at the same time. So there's no carbocation intermediate. In Sn1, the leaving group leaves first, and then the bond is made from the nucleophile, so that there is a difference. Because I make a carbocation intermediate, I know that the tertiary carbocation is going to be more stable than the secondary carbocation. Let's take a moment to briefly review that fact and to once again explain why this occurs and how this occurs. Let's say for a moment that I'm performing the following hydrolysis reaction to make an alcohol. In the first step of the mechanism, we know that the carbon-bromine bond will dissociate. This gives a secondary carbocation. Now hopefully, if I've done my job, I've convinced you that you should always be paranoid of a 1,2 hydride or a 1,2 alkyl shift. And so we can get a 1,2 hydride shift to generate a more stable carbocation. The question is, how do we know that the carbocation rendered in green is more stable than the carbocation rendered in white? To do this, we need to take a closer look at the orbitals, and so let's do that. In the carbocation rendered in green, we have our carbocation, which I'm going to render in with this green dot. We have a methyl group. And I'm going to emphasize one of the carbon-hydrogen bond orbital overlaps. And so there are a pair of electrons in this bond. Carbon is more electronegative than hydrogen by just a bit. I also have another methyl group, and again I'm going to emphasize one of those carbon-hydrogen bonds in terms of the orbital overlap. And I have a third carbon to which it's bonded. And I have a third source of a carbon atom more electronegative than a hydrogen atom. It means this bond is very slightly polarized. And we have a p orbital that's coming out of the plane of this screen directly towards us and directly away from us. And so these electrons are able to be weakly donated to help stabilize this empty p orbital, both from the front side and from the back side. And of course, if one of these orbitals is coming out of the plane of the screen, it's easy to rationalize it overlapping with the orbital coming towards us. But you also have to remember that this is tetrahedral geometry, and we can easily visualize this happening from the back end as well. The ability of these carbon atoms to use their sigma electrons and weakly donate them and stabilize a p orbital is termed hyperconjugation. Hyperconjugation is really inductive effect. But rather looking at the electronegativity of the atoms, it's the ability of those polarized electrons in the bonding orbital to overlap with the non-bonding empty p orbital of the carbocation. This is more significant when you have 3 sources of sigma bonds. Therefore, tertiary carbocations have more of this sigma overlap than secondary carbocations. And again, primary carbocations, this is done to such a small extent that we've really never isolated a primary carbocation in biological systems. And if we were able to isolate them, when you start comparing it with the fact of how many times we've isolated a tertiary or a secondary, we still realize that these are the 2 workhorses of SN2 reactions, or excuse me, of SN1 reactions. Making a tertiary carbocation, making a secondary carbocation. So the rank order of the substrate selectivity is that if we have a tertiary carbocation, it will exclusively be SN1. Number 1, I've got a carbocation intermediate. Number 2, it's too bulky for SN2. And from the last podcast, we realized that if we have methyl or if we have primary, it's going to follow the Sn2 mechanism. So really the only mystery is what happens with the secondary substrate. And we will be looking at this week in class, and it's going to be due to the solvent effects. So secondary can go either SN2 or SN1, and it really depends on the solvent effects of the system. Now let's look at some free energies free energy diagrams, and let's particularly focus on the energy of activation for the slow step. So to your left on slide 718, you see that the energy of activation for a secondary substrate, in other words, to generate a secondary carbocation, is much greater than the diagram on the right with a tertiary substrate to generate a tertiary carbocation. In other words, since they're more stable, they'll be formed faster. And notice the annotation at the bottom of the slide. The primary substrates react too slowly to even measure them. This, of course, is consistent with our hyperconjugative theory that tertiaries result in better orbital overlap than secondary, than primary. So we're basing, in part, this hyperconjugative theory with the experimental observations, that is, the experimental facts, that we don't isolate primary carbocations in nature. If they do occur, they're certainly not measurable. Now, the stereochemistry, again, this is Klein's representation. I think it works very, very well. We can have approach from the front orbital or the red orbital. And if we do this, we will maintain the stereochemistry. So when it attacks, it pushes the propyl, the methyl, and the ethyl back to where it was. Or I can attack from the back side. And if I attack from the back side, it's going to push the propyl, the methyl, and the ethyl to the right, which inverts it from its original configuration. Since I do this to equal amounts, I should get an equal amount of R and an equal amount of S. Notice in this particular example, bromine would be priority 1, propyl 2, ethyl 3, methyl 4. The low priority is already oriented away from us for convenience, and this is going to be S. S reactant, mixture of S and R in the product. Now, I feel compelled to tell you that the truth is, usually we find we don't exactly have this 50-50 mixture, but in a molecule such as this, it's going to be really, really close to 50-50. Again, the more bulk I have, the more unreasonably complicated it is, then the more it would deviate from this 50-50. So we might see something like 52-48 or 51-49. But on paper and on an exam, unless it has a significant amount of bulk, you would report an equal amount of both enantiomers, therefore it would be a racemic mixture and have no net optical activity. If we place this into a polarimeter, theoretically, the angle we measure will be 0 degrees. If it's an Sn2 reaction, it will have a net optical activity because we have a net inversion of the chiral center. So let's look at an example where we do have some bulk. So on slide 720, we see that we have 1, 2, 3, S, 2-chloro, 4-methylpentane. I'm going to react this with NaOH, and I get a net inversion. This cannot react by the Sn1 mechanism. This has reacted by the Sn2 mechanism, and we know that it's reacted by Sn2 because of the net inversion, because I'll have net optical activity. Now, in the second line of this slide, Klein makes a very interesting point. He asks, is it reacting more by Sn1 or Sn2? On paper, in lecture, on podcasts, I'm talking about these reactions like they have a choice. It's 100% Sn1 or it's 100% Sn2. Fact of the matter is that nature's more complicated than this. These have elements of both. Therefore, the proper result, or the proper interpretation of this data would be this reaction proceeds more by Sn2 than it does by Sn1 because of the stereochemical result that we measure in an experiment, that we measure in the lab, that we observe, that is a fact. This is no longer theory, but rather fact. Okay? So we can compare these Sn1 and Sn2s in terms of mechanism, energy diagram, the kinetic integrated rate law, the rate of the reaction with regard to the substrates, or the stereochemistry. So notice in Sn2, it's one-stop shop. It's a concerted mechanism. There is only a transition state that's observed, no intermediate. It's dependent both on the rate of the substrate and also the concentration of the nucleophile. The methyl and primary substrates are more reactive than the secondary or tertiary substrates. And the stereochemistry gives me an inversion of configuration. Sn1 is different in every one of these metrics. It is a stepwise mechanism occurring in steps. Because of that, we have a carbocation intermediate that can rearrange. There is no rearrangement in an Sn2 reaction. The kinetics depends upon only the concentration of substrate. And by the way, this gives a great laboratory mechanism to differentiate between an Sn1 and an Sn2. Namely, start collecting kinetics data, and if you change the concentration of the nucleophile, but the rate doesn't change, it's got to be Sn1. But if you double the concentration of the nucleophile and the rate doubles, it's got to be Sn2. If you double the concentration of the nucleophile and the rate increases by a factor of 1.5, it's basically 50% Sn2 and 50% Sn1. So this leads to some really great inquiry experiments that we could do in the lab to explore whether a reaction is truly Sn1 or Sn2, and I will be giving you all an opportunity to do this in the laboratory. Of course, the substrates are inverted because of carbocation stability, and we essentially form racemic mixtures. Now, Klein says with slight preference for inversion due to ion pairs. I think it really depends on what the structure of that initial reactant is going to be. But on paper, just to be clear, they form racemic mixtures unless I give you a really bulky initial substrate. So we'll be talking about this more in class this week. This gives you a really nice head start on the theory that's going to be required for Sn1 and Sn2. What remains are going to be solvent effects and effects of nucleophiles, and we'll be exploring that more this week.